Thank you. Yeah, so I will present a formal analysis of 5G authentication. And it's a joint work with David Bazin, Yannick Dreyer here, Sasha Radomirovic, Ralph Sasse, and Vincent Stedler. All right, so let's start by discussing a bit the process of designing security protocols. So very often it starts with smart people, for example, those people here from IETF on the left, who discuss, and at some point they come up with a standard, let's say for TLS. And this is then released, implemented, deployed, so that happy users like this guy on the right can do banking securely, for example. So this is all very nice, but in practice, there are all those small people out there, and some of them are trying to break those protocols for good or bad purposes. So now the story is a bit different. A first attack will be found on the protocol. So now the user is wondering whether it's safe or not. But the designers are reassuring at this point. They just say, we'll fix that, and they provide a V2, a version 2 of the standard, that fixes this first attack. But then a second attack, sometime later, a second attack will be found on the same protocol, on version 2. But the designers are still saying, we'll fix that, and now they provide a version 3. And at this point, the user might be a bit skeptical, and I can understand that. Later, maybe a third attack will be found, and I will stop here because I think you got the idea. There is no end to it. This is like an infinite cycle, so it's pretty bad. But don't get me wrong here. I'm not saying that this is because the designers are not smart enough. I would rather say that this is an asymmetric fight. Attackers on the right are only looking for the weakest link. That's much easier to do. While the designers have to come up with protocols that have to cope with many complex things. So an active adversary, an insecure network, concurrency, backward compatibility, so on and so forth. So it's really hard. So now the question is, how can we help those designers? And this is where formal methods come to the rescue. So using formal methods and formal verifiers, those designers could automatically find errors and attacks quickly and early in the process. They could also establish formal security guarantees on the protocols they design. And finally, using such techniques, one would have to be explicit about the system and the environment specification, but also the security goals that are expected to hold, which is a good thing, being precise about those things. And the goal of this work will be to apply such formal methods to 5G. Okay, but why do we even care about 5G in the first place? So first, mobile communication is ubiquitous, as you may know. There are almost 5 billion users in the world, and 60% of the world population has access to 4G. But the next big evolution will be 5G. So 5G is designed by 3GPP, who was also responsible for 3G and 4G. And this technology will be deployed in 2 phases. And in this work, in this talk, we'll be focusing on the first phase. So for that phase, the standard has been frozen last summer, and the commercial service will start in 2020. So regarding authentication, one of the key protocols in 5G is AKA. And the goal of AKA is twofold. First, it should establish a secure channel between a phone and the antenna that the phone is trying to attach to, and also mutually authenticate those two entities. So there have been different versions of AKA from 3G to 5G, and in this talk, we'll be focusing on 5G AKA. So this protocol is supposed to improve security prior to generations, but very little is provided in the standard to back up this claim. So now the questions that are interesting are, what are the security goals that are exactly provided by this protocol, and under which threat model and security assumptions do you get those properties? And we'd like to precisely answer to those questions in a systematic and rigorous way using formal methods. So we took the standard and we used state-of-the-art formal verifiers to conduct a security evaluation of 5G AKA. All right. So let me give you some ideas about the formal model we use to do this formal analysis. So we use a so-called symbolic model, also called Dole-Viao model. And one of the main ideas of such a model is to abstract away the cryptographic primitives. So we'll be assuming that they perfectly achieve their goals, which doesn't mean that the big protocol using those primitives as building blocks is secure. So we still have to verify something. So we model those security protocols in a formal language with a proper syntax and semantics. That also describes a very powerful attacker who controls all the network. So he can learn all protocol output and he can choose all protocol input. And finally, security properties will be encoded as reachability or equivalence properties. So one of the main benefits of such an abstract model is high level of automation we can achieve with the tools and techniques for verifying properties. So the goal will be to target and hopefully reach this sweet spot between precision of the guarantees one can establish and automation of the proofs. And I have to say that automation is critical here because of the size of the protocol. It's just too big, too complex. So there are many efficient procedures and tools for verifying such properties. Note, however, that the underlying problem is undecidable. But in this work, we have used the tool Tamarin. So this guy here, corner top right, that is the only tool that can deal with all the required features of 5GAK. So what have we done? So we read the 5G standard, so huge amount of text, and despite that, we found that there are some, a lot of things are implicit, unclear, underspecified. So first, we had to formalize this and come up with a precise system specification. And only from there, we could build a formal model of the system and of the properties, all the properties, a formal model in the Tamarin language. And those we could give to the tool, to the Tamarin tool. And we obtain automatically for each single property either an attack or a proof, or maybe the tool does not terminate. And this is to be expected because, as I said, the problem is undecidable. But because this protocol, the 5GAK protocol, is really complex and quite large, we obtain such non-termination cases a lot. So we had to come up with proof strategies that are sound by design, but that help the proof search. So it doesn't impact soundness and competence, but using such techniques, you can just get rid of those non-termination cases. So we managed to do that. And then when we found attacks, we design fixes for those attacks, and we use a tool Tamarin to make sure that those fixes actually fix the protocol. So those are provably secure fixes. So finally, the attacks we found and the proofs we established and the fixes we designed all together form what we believe is a comprehensive security evaluation of 5GAK. So what are the contributions in more details? So when we formalize the standard, we have identified key missing security goals and flaws in the stated goals from the standard. And we propose instead a fine-grained variant of goals in terms of secrecy, authentication, and privacy. We also provide the first faithful model of an AKA protocol. And for that, we had to tackle some challenges related to 5GAK, like the loops, the state machine, the scale of the protocol, and the use of XOR, which is actually hard to reason about in the symbolic model. And we also provide dedicated proof strategies in Tamarin to reason about the protocol and have automatic proofs. And thanks to all that, we were able to do this security evaluation of 5GAK. And our goal was to actually identify the minimal security assumptions that are required for each security goal to hold. So we were able to be really precise about what you need to get those properties. And we found out that some critical authentication properties were violated. We found that privacy is preserved for a passive attacker, but broken for an active attacker. And we proved that secrecy holds, but not perfect forward secrecy. And finally, we provide explicit recommendations and provably secure fixes that very often also simplify the protocol. All right, so let me introduce very briefly 5GAK, the protocol we have verified. So the goal of 5GAK is twofold. First, it should mutually authenticate a user equipment on the left, so essentially a phone with a SIM card, with the corresponding user's carrier, the user network provider. I will call that home network, so on the right. And this protocol should also establish session keys between the same user equipment and the serving network in the middle, which is essentially the antenna that the phone is trying to attach to. And note that serving network and home network might be different. Think, for example, about roaming situations. That's one example. All right, so to achieve those two goals, the protocol will rely on a bunch of shared data shared between the user equipment and the home network. So first, a permanent user equipment identifier called SUPI. I will call it SUPI. A symmetric key K that will be used as a shared secret, and a sequence number SQN that will be used for replay protection for the user equipment. And yeah, user equipment also knows the home network's public key, PKHN. So now I will try to explain to you the core logic of the protocol. I won't give you the full details, it's just too big, too complex, but just, the core logic of the protocol. So first, the user equipment will identify itself towards the home network on the right by sending his identifier SUPI, but encrypted with the public key of the home network. Based on SUPI, the home network will start a challenge response mechanism with the user equipment, so the blue boxes and the green box. But because the user equipment does not participate in the randomness of the challenge, the user equipment will use the sequence number as a way to protect from replay protection, to protect from a replay challenges. So it's essentially a it's essentially a challenge response mechanism based on the sequence number for replay protection. And I hope it's going to be enough for the rest of the talk. Note, however, that because those two parties use the sequence number for the challenge response, and because the sequence number may become out of sync, there is a resynchronization mechanism where the user equipment sends in a protected way the sequence number to the home network. All right, and yeah, as I said, this is overly simplified, but should be enough for the rest of the talk. So I won't describe that. All right, so I will skip the formalization step, and I will directly go to the modeling step, where we formally model the precise system specification in the Tamarin language. So we modeled 5JK with the full state machine, with the resynchronization mechanism, which is important and can be a source of attacks, and with a precise modeling of XOR and of the counter sequence number. And this is because, and that's why we use Tamarin, because that's the only tool that can deal with all those features here. We also modeled this optional key confirmation round trip between user equipment and serving network. And we model all that for an unbounded number of user equipments, serving networks, and home networks, and an unbounded number of sessions of each such entity. So kind of the worst case scenario. We also consider these honest user equipments, these honest serving networks, these honest home networks. Next, we model the security goals. So our basic threat model is this powerful DOLEV Yahoo attacker who controls all the network. And we model a wide range of formal security goals. So secrecy, some secrecy, some authentication, and some privacy properties. And for each such property, we model variants, different variants of the properties that capture different compromise scenarios. Because as I said, our goal will be to identify the minimal security assumptions or the strongest possible attacker model you can have while still getting the property. That's why we had to model many variants of security goals to capture that. So as I said before, because of the complex state changes and all the loops in the protocol, the fully automatic mode in Tamarin rarely terminates. And fully manual proofs are just impractical. So we needed something in the middle, kind of. So we came up with those proof strategies. So essentially intermediate lemmas with invariants of the protocol, and also heuristics that guide the proof search. All right, so now I can tell you more about part of our results, part of the results of our security evaluation. So first, why do I need to tell more about why it's just not as simple as saying the protocol is broken or the protocol is secure? So let's take authentication properties, for example. So first, authentication depends on the perspectives you want to consider. So who obtains the guarantee and about whom? So in a sense, you want to consider all different pairs of parties. So I'm building a table at the bottom that will describe what we want. But authentication also depends on the kind of agreement you want. Do you want to agree on, the two entities you're considering, do you want them to agree on identities only? Do you want to make sure that they agree on the data as well? Do you want replay protection? You have a bunch of different agreement properties, and you may want to consider all of them. That's what we want actually. And finally, for each such property, you may want to consider different attacker models. What can be compromised in your threat model? So that was our goal. We wanted to capture all those different variants. That's why we took this systematic approach where we can, in a sense, fill in the table at the bottom. And for each single cell, we can say, okay, the shared symmetric key should not be compromised, but everything else can be compromised and you still get the property. We want this kind of information in the end. And thanks to this systematic approach, we were able to find a bunch of attacks. And that's the first one we found. So we found that an attacker can make a service network think he's talking to another user equipment, to a wrong user equipment. So in a sense, they don't agree on SUPI, on the user equipment identifier. So how is this possible? So the main reason is that the home network will send to the service network the session key and the SUPI in two different messages, and those two messages are not bound together. Which means that the attacker can interleave two sessions coming from two different user equipments, and at the end, it will just swap the SUPI sent in the end, so that the service network will assign the wrong SUPI to a given user equipment. So that's why this attack is possible. And interestingly, this attack was not possible in a previous strat from last March, because before, those two messages were sent together. And we have actually detected this attack when we updated our model with regard to the new version of the standard. So to fix that, we propose two solutions. So first, you can explicitly assume in the standard that the channel between service network and home network is a binding channel, meaning that the lower layer will ensure you that all messages sent in a session are bound together, kind of. Or you can just cryptographically bind the messages together, and we give all details in the paper. Okay, next we verified again all properties with one of those two fixes. And we found that key confirmation, so this optional key confirmation phase, was actually among the minimal required assumptions. So key confirmation is required for critical properties to hold, but key confirmation is not mandatory in the standard. So that leads me to the second attack. So we found that an attacker can impersonate a service network towards user equipment without or before this key confirmation, which is not mandatory in the standard. And again, the reason for that is because the service network name that identifies a service network is not included in the MAC sent by the home network to the user equipment with the challenge. So in a sense, the user equipment, the phone, has no proof that he agrees on the service network name with the home network. So he doesn't know if he's talking to a service network that has been authorized by his home network. So to fix that, again, you can add in the standard that you can precise that the key confirmation should be mandatory, is mandatory. Note, however, that we've proven that only one direction of this key confirmation is actually required. You don't need the other one to get the property. Or even better, and that's another fix, you can add the service network name to the MAC sent by the home network to the user equipment. And if you do so, you don't need the key confirmation anymore. You don't need it for authentication properties. So yeah, those two fixes actually simplify the protocol and the number of round trip. Okay, so we've proved that secrecy holds, but not perfect forward secrecy on the session keys. And regarding privacy, we have proven that the user equipment identifier SUPI remains secret. meaning that the good old IMSI catchers in 3G and 4G no longer work in 5G, at least in the current state of the standard, which is great. But unfortunately, this is not enough to make sure that users are not traceable for an active attacker. And we actually found an attack that was still valid in 3G and 4G, and that will be one could exploit this attack in 5G as well, at least in the current state of the standard, that allows an active attacker to trace user equipment. And the problem here is that fixing that would require a major redesign of the standard, so we are not super hopeful that this will go to the standard before deployment, at least for phase 1. Okay, so we formalize the 5G standard. We provide a Tamarin model for 5G AK with proof techniques, and we provide this comprehensive security evaluation of the protocol. We found that the 5G AK standard lacks explicit security assumptions and security goals, but in the end, the standard does meet the core properties when you add those easy fixes and those missing assumptions in the standard. So it's okay in the end. It can be fixed quite easily. But even though the standard has improved privacy over prior generations, so because the SUPI is not sent in the clear text and stuff like that, even though it's better, 5G will still suffer from traceability attacks, which is quite sad. So we have an ongoing discussion with 3GPP and GSMA, and they told us that they will add part of our fixes to the standard. But I mean, this is ongoing discussion. Future work. So we plan to verify and formally compare the different variants of AK, because there are like tons of variants for 3G, 4G, even 5G has 2 different variants. So how do they compare to each other? We will definitely follow the development of 5G, notably phase 2, and keep our model and our evaluation up to date. And finally, we would like to improve the way privacy is verified in Tamarin, both from a precision and efficiency perspective. And yeah, finally, future work for designers maybe. So I would say that formal methods are a powerful tool, and recently it became major enough for the real world. So why not using such a tool more often now? And I will just conclude with that. So we've done this, we took the standard ourselves and used formal methods to do the evaluation. And hopefully in the near future, we can see more examples like this at the bottom, where designers directly use those tools to do the verification prior to standardization. TLS 103 is one great example of that, for example. And I'm done here. Thank you.
Hi, Yan Chen from Northwestern. Very interesting work. I wonder, the 5G is very big particles. So beside AKA, is there anything else that you have been looking at, or you can plan to do for using formal method for verifications?
There are a ton of protocols. So there are protocols prior to authentication. Those are interested, but anyone can impersonate the network because it's prior to authentication. But still, it's interesting to look at those. And after authentication, someone should look at those protocols as well, because even if you have authentication, maybe secrecy or other properties or privacy can still be broken. We haven't looked at it, but yeah,
Okay, thank you. Second question is, I know you use the tool you claim to be very precise, but did you make any simplifications when you model the protocols? Do you think that can, hide any vulnerabilities?
So we use the symbolic model. So we have to abstract away the crypto, for example. So that's one simplification. But then we've tried to be as conservative as possible regarding the logic of the protocol. So it's pretty precise in the end. But we prove guarantees in a symbolic model which abstract away primitive. So that's one big approximation we do.
Thank you.
Hi. First, thanks a lot for your presentation, really interesting work.
Thanks.
I've been working for 3GPP as a standardization delegate for some time, and I really agree that it would be great if formal methods would be used, in the process of standardization. But I'm wondering, like, if you have any idea how this could really be used in like the real world, because you have now this model in Tamarin, and if the delegates would really have to use it, they would kind of have to learn a new programming language. And okay, now you have modeled this AKA, but how realistic would it be, like, if they would try to assess some feature building on top of this, that they would like maybe change your model?
Yeah. So yeah, it's a good point, because I mean, here the designers have to understand the tool, right? So yeah, so I mean, so we are improving the way we can use the tool and usability, and the fact, for example, the fact that you have to come up with those proof techniques. That's hard. For that, you need to understand the tool and the internal of the tool. So yeah, I definitely agree here. But on the other hand, I mean, the standardization took a few years with 50 plus people for at least for those protocols. So maybe it's worth spending maybe 1-2 people looking at that sometimes, and we can help as well. So yeah, it takes time, but I think it's really valuable and you get a lot. So yeah.
Yeah. No, I definitely think so too. I really hope that we would somehow find a way.
Yeah, great. I mean, great.
Let's. All right. Thanks.
Thank you.
So I'm Yongdae Kim from KAIST, and I've been working on cellular networks a lot, especially breaking things. Anyway, so can you compare, in terms of security, can you compare your work with the Oxford report, Cas Kramer's?
Okay, customers here. So yeah, definitely. So interrupt me if I'm saying something more. So essentially, they looked at kind of a different direction. So they consider 2 sub-parties inside our network and explore what can go wrong when you separate those 2 parties. And they found an attack that is similar to the first attack I explained, where a channel was not binding and you could swap 2 messages and that could lead to an attack.
So having, I mean, assuming one more entity, I mean, like separating those 2 entities are the main difference?
Okay, so it's better, but on the other hand, it's hard to combine the 2. So we've been discussing that, and just to be clear, we use the same basic model. So we are not duplicating effort too much. We use the same basic model, but then we went to a different direction, and they went to another direction. But now, yeah, it would be great to merge those 2 and see what we get when we have 4 parties instead of 3, essentially. But it's already really hard in terms of proofs. So yeah, definitely a future work. But
and one more question.
Yeah.
So when you look at actually 3GPP standard, there are like a huge number of protocols, right? NAS, you know, and in LTE there are NAS and
different
and each of the standard has actually a lot of options too, and sometimes those options actually conflicts, right? Well, I mean, probably it's related with her question that, you know, how realistic is it to actually using formal model to actually verify the entire like
the entire ecosystem,
including the options, because there are so many options, and actually sometimes those options actually conflicts. And in terms of the formal model, I mean, is there any cheaper to, because you had to simplify some of the design?
Yes. Oh yeah, sorry, yeah. Okay, key confirmation might be you could think about key confirmation as an option. And we explored the 2 possibilities, with or without, and we found out that it's not an option. You need it to get the properties. So it's possible.
But the entire
yeah,
like
no, entire, yeah, okay, it's a huge effort. So if we all, I mean, if we were 50 researchers, maybe, I mean, yeah, okay.
So in the interest of time, thanks.
Yeah, thank you.
Place to kind of continue the coffee break. Thanks very much.
Thank you.